Hello, how's it going, everybody? Let me just double check everything's working. Okay, yeah, it seems like we're live. Hello, how's it going, everybody? Okay, perfect. Welcome to another episode of the console logs. I don't think the music's too loud, is it? Should be fine. Okay, so today we're gonna be solving some lead code questions, some DSA questions. We're back. This is what is it? It's the second week doing this? No, it's the third. Yeah, it's the third week of stream. And like I said, we're just gonna keep solving some DSA questions from Grind 75. Yeah, probably just get right into it. I don't have any cool stories this weekend. I mean, actually, maybe I do. I started moving out of my place because I'm moving to a big city in June. So I started like packing stuff from my place, starting selling some furniture and stuff. So that's what my weekend sort of looked like, and I went out with some friends and stuff. But yeah, today we're gonna be solving some DSA. But before that, and also like here behind, like change the background as I always do. I have this time the set from the Big Bang Theory, the broken elevator, the stairs from the apartment building. Yeah. But yeah. Before we start, we'll just do the Lorcana card of the day like we always do. So let me switch back to the scene. And today we have a Gadget Hack Wrench. It's a 4-cost inkable. Gadget Hack Wrench, Quirky Scientist. It has 3 strength, 2 willpower. It's a Storyborn ally inventor. And it says when you play this character, if an opponent has more cards in their hand than you, you may draw a card. This card is pretty. It's okay. I don't know if it's seen in a lot of decks. So let's actually look it up. So it's a gadget hack wrench. This one. Usually it appears down here if it's in any deck. I think so, at least. Yeah, this is what it appears. So maybe it's not in any decks, or maybe it just didn't load properly. It's probably not in any decks. It's not horrible. Like if you get it in draft. So normally when like sets release, in Lorcana, they do like what's called a draft. And the draft is basically like you go in to try to test like the cards from the new set. You open some packs and play with whatever cards you get, and everybody plays with like the random cards. And so if you get this as a draft, it's not the worst thing in the world. Like you get to draw a card if your opponent has more cards than you. Quest for 2. It's a 3/2. I mean the 3/2 for a 4 cost is not amazing, but it's pretty decent. The artist here is Lisanne Coetu. It's card 99 out of 204 in English. It's from set 8. This is Reign of Jafar. It's a rare. I think that's what this is, and this is Lorcana. And I like the art. I think this is from the maybe not from the Rescuers. Let's see. Gadget Hack Wrench. Oh yeah. Oh no, the Rescue Rangers. This is different. I need to watch the Rescue Rangers because there's a Zipper is a character that they've released a lot of cards for. Monterey Jack. The Rescue Rangers. Oh, what did I just type? Okay. It was Chip and Dale. Ah, look at that. Maybe I'll watch it sometime. But okay, I'll just try to get some lead code problems done. But just before that, I'm just gonna go grab some water because I forgot to bring any, and it's gonna be a long session, so I'll be back in a sec. I'm back. Got the water. Oh. Okay, let's see what's in store for us. Implement queue using stacks. Okay, I remember this one. It says, okay, I might have to do some explanation. I've already explained stacks in the past, but I'll go over it again, and queues as well, but I'll go over it again, how we're going to solve this. But 232, implement queue using stacks. Implement a first in, first out queue using only 2 stacks. The implemented queue should support all the functions of a normal queue: push, peek, pop, and empty. Implement the myQueue class. You have push, which pushes an element to the back of the queue, pop, which pops it from the front, peek, which lets you see the front, and empty, which returns true if it's empty and false otherwise. You must only use standard operations of a stack, which means only push to top, peek from top, size, and empty. Depending on your language, the stack may not be supported natively. You may simulate a stack using a list or dequeue, as long as you use only a stack standard operations. Okay, so we're gonna use 2 stacks to implement a queue, and let's go over like what a stack and a queue is and how they differ from one another. So they're both data structures, so it's meant to store some sort of data, and they have some restrictions in the way you can insert to it and retrieve information from it, so that it's more efficient or better to use in some occasions. So I'll just separate this in 2 halves. So this is gonna be the stack versus, oh my god, that line was not straight at all, the queue. So in a stack, as I explained the first time when we were doing the parentheses problem, the valid parentheses problem, a stack, it's like if you have a stack of plates. And it's a first in, first out operation, right? Oh no, sorry. First in, first out is the queue. That's yeah, that makes more sense. I was like, that doesn't make a lot of sense. Actually, a stack is a last in, first out structure, a LIFO structure, while a queue is a first in, first out structure. And let's explain a little bit about what the differences are. So we're gonna say in this like stack and queue, we're gonna store numbers. For now, to simplify, you can store any sort of information, but for now we're just gonna store numbers. So as I mentioned before, in a stack, it's like if you had a stack of plates, right? So when you have a stack of dishes or plates, you put them on top of each other in your cupboard. And when you're trying to take one of the plates out, let's consider that all of the plates are the same. You take them out from the top, right? So because it's easier, you have easy access to it. So if you think about it, the last plate that you put in the cupboard is the first place that you end up taking out. That's why it's last in, first out. The last element that you put in is the first you take out. So in your cupboard, you put the plates one on top of the other. The one that you put at the top is the one that you put there most recently, and it's the one that you're gonna take out when you're trying to take out from it. You don't take out from the middle, you don't take out from the bottom, you take out from the top. That's why it's called a stack. So we're gonna have, I'm just gonna represent it here. Let's do something like this. So let's say we insert, like we said, we're inserting numbers. So we're gonna insert the number 1, then the number 2, then the number 3. When we're gonna take them out, we would take out 3, then 2, then 1. We take them out in that order. So the most recent goes out first. In a queue, it's a little bit different. So in a queue, it's similar to how you would have a queue in a bank. The first person to line up is the first person to get attended, or the first person to get out in this case. That's why it's first in, first out. The first person that was in is the first person that we take out. In this case with numbers, I'm not going to draw it vertically. Let's draw it horizontally because it makes a little bit more sense. So let's say we put in 1, then 2, then 3. Then we take them out in that order. We take them out 1, then 2, then 3, because 1 we added there first, then 2, then 3. We take them out in the order we put them in. Whereas in here, we take them in reverse order. We take them out in the reverse order. Yeah. And so our task here is to be able to implement the functionality of a queue, which in naming it would be pushing something to the queue, like putting something at the end of the queue, popping something from the queue, so taking out something from the beginning of the queue. We also need to implement empty to check if it's empty. That should be pretty simple. And peek, which just returns the top of the stack. Now, if we think about both of these data structures, you can see that the only thing that matters here is like the way we take out elements from it. And you're gonna see that this is in reverse order from this. So we must find a way to use both stacks to reverse the order of them, so that when we take them out in the order we want them in the queue. Because it doesn't matter how we store them. It just matters that when we take them out in chronological order. So the first one that was in is the first one that comes out. So we must find some sort of way to use the stack to be able to reverse the order of the, use two stacks to be able to reverse the order of the elements before we take them out or we peek from them, right? So let's think about how we would do that. So we have here stack 1, and we have here stack 2. And I'm just gonna draw them both here vertically. Now let's see the example. I don't know if I'm gonna be able to copy and paste it here, maybe? Definitely not. Okay. Oh, actually if I do that, yeah, perfect. So we receive the following operations. So we create a new queue, then we push a 1 to the queue. I'm just gonna draw first with how like the operations would go in a queue. So we push a 1 to it, then we push a 2. Now we peek. The front of the queue should be the 1. Now we pop the 1, and now we check if it's empty. It's false because the 2 is still there. So to start with the simple stuff, for creating the queue, we just basically create 2 stacks, and they're empty at the beginning. For checking if it's empty, we check if both stacks are empty, and if they're both empty, that means our queue is empty. Now, the part that's hard here is how we're gonna push and pop from the stack. I mean, we can, like we said, it doesn't matter how we store them as long as we get them out in the right order. So let's say for now, and I think that's the final answer, but I want to work this answer through. We're gonna put them in like one of the stacks just in order. So we put here 1, and we then put 2. Now, if we want to get them out, we know we need to reverse this order. So it's 2 and then 1, right? Because we want the 1 to be at the top, because that's the one we're gonna have to take. So what we're gonna have to do for this is basically reverse. Yeah, we're gonna have to reverse it. And how do we reverse it? Well, if you think about it, if you're putting all of the stack, let's go back to the cupboard example. You have all of your plates in one cupboard, and let's say you're trying to move from one cupboard to the other, and you take the top plate and you put it at the bottom of the cupboard, and you put the top plate and you put it on top of the first plate that you put in. So if you keep doing this, the order of the plates, let's say they're all different colors, the order of the plates is going to be reversed. So this is how we're going to reverse the order to be able to return it for our queue. But you have to think about another thing. Okay, so let's first solve the problem of like popping. So when we're gonna pop, let's say we have here, we put the 1, the 2, and the 3. We need to take out the 1. So what we're gonna do is we're gonna empty all of the contents from one stack to the other. We're gonna go 3 is gonna go here. Then 2 is gonna go here. And then 1 is gonna go here. And now we can check if we're doing the peek operation, we can check the top of the stack, or if we're gonna pop, we can pop from the top of the stack as normal. Now, when we need to insert again, we can't just, like, okay, let's say we've removed this one. And we removed this one, and we know there's a 3 here. This is the queue representation. This is our stack representation. So we've removed the one here, and let's say now we add like a 4. We can't just add it here at the top, because the 4 should not be at the top of the stack. The 4 would go at the bottom of the stack, at the end of the queue, because it's the one that was inserted the most recently. So what we need to do is we need to reverse back the order. So if you think about it, we're gonna have a stack for inserting and a stack for peeking and popping. When we are inserting, we insert them on the left stack, let's say. And then when we're popping, we're gonna empty all of the left stack into the right stack and take the top. When we're peeking or popping. And then when you're gonna need to insert again, we need to reverse back the order. So we empty all of the contents from the right stack again into the left stack. Yeah? And so that process is going to be more slow than a regular queue, because in a queue you just do all of these operations in O of 1. In this one, every time you switch between operations, you have to do an O of n operation where you empty the stack from one place to the other. But that's what they asked from us. And if we check the constraints, as long as the n is not like too big, so at most 100 calls will be made, and x. What is x? What is x? X is like the element that you're gonna put, but it doesn't say how many elements are gonna be in here. But it should be fine. Let's check the follow-up just in the meanwhile. Okay. It says, can you implement the queue such that each operation is amortized O of 1 time complexity? In other words, performing n operations will take overall O of n time, even if one of those operations may take longer. So I think this is a little bit of what I was talking about, in that if you call push, then pop, then push, then pop, then it's gonna basically like empty into this side, then empty into this side, then empty into this side. So that's gonna take O of n each time you do it. And like now that I am thinking about it, I don't know how, like, if the solution that we're doing would satisfy this. We can check the solution after to make sure to just check if there's a better solution. There might be a way that we don't have to like empty all of it at the same time. Let's think a little bit about that. Oh, I think I know. Okay, so let's go back to the example. Here, we can make this a little bit better. So before we're talking about every time we insert, we just empty into one side and like leave the other side. But we can make an improvement on this. Let me just delete this. Just delete the whole thing. So this is gonna be my stack 1 and my stack 2. And let's say again we add 1, then 2, then 3. Then we need to remove the top, so we're gonna empty all of it into here. We have to, because we need to get the bottom element, the bottom element anyway. Sorry, this would get reversed. So this would be 3, then 2, then 1. So now we've emptied this side, and the right side is in the right order we want. So let's say we deleted this one right here. Now when we insert a new element, we don't need to, I'm gonna lower the music a little bit, it's a little bit distracting. Just lower it from here. Okay, so when we add a new element, we don't need to like empty the whole thing here and then add the element. What we can do is just add the element in here, right? So we're gonna like consume so we're gonna do what we were saying before, where we insert here and we pop and peek from here. But when we're doing the insertion, we're not gonna reverse the whole thing and add on to it. We don't have to, because we've already consumed this and we already know that this is gonna be in the order of the queue. So what we're gonna do is we're gonna, whenever we do pop and peek, we're gonna try to like consume from the top of this queue. And if it's empty, then we're gonna need to do the reversal operation. We're gonna need to move everything from here to here, right? But if it's not empty, we can just keep taking from the top. Because, okay, we had like 1, 2, 3, 4, 5, right? So we inserted the 3. Then we removed from the top, and then we added 4 and 5. We can just add 4 and 5 here, and we consume from the right stack until we're empty. Once we're empty, we reverse all of everything we have here. So that way we don't have to like reverse and reverse and reverse and reverse, because that's a very expensive operation. We only need to reverse as long as we need something to pop or peek. Otherwise, we can just store the information as is. And I think that should be an optimization of what we're doing recently. We were doing before, because we're only doing this for the amount of we're only reversing for the amount of elements that they're asking of us. I don't know if I explained that well. But if you think about it, we only have to reverse it when they ask where they ask us for an element for pop or peeking, and we don't have any elements to consume from here. So that I don't know like how to calculate the complexity of that. I think it is probably amortized like O of 1. Because you could like insert a lot of operations here and then ask for 1, so then it would have to reverse the whole thing and then get the top, which would be O of n total. Yeah. So you would do this operation of like putting stuff here, you would do it O of n times total. Because either you insert a bunch of elements and then ask for 1, or you insert some elements, put them here, then keep consuming from here, then insert some other elements and put them here. At the end, you're only gonna do the operation of like reversing for n elements at most. So it would be O of n amortized. So yeah, I think we got the solution pretty much figured out. Let's go and code it up. Oh, no thanks. Close. Okay. Let's go to lead code. And now this would be stack. Do we have a queue? This is like a stack problem. Let's put it as a stack problem. It's a stack or queue problem, and honestly probably doesn't matter. Let's see what the topic is. Stack design queue. Yeah, so honestly, let's just put it as a stack problem. And vim stack 232.cpp. Let's just get back this beautiful background. Okay. So let's see. Let me copy this whole thing. Bum, ba, 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 bum, bum. Okay, so when we're creating the queue here, I don't remember how classes in C++ work, but I think I could probably have I think you can have like a variable here. So here we would have stack of int, and then it's gonna be stack of int. We're gonna have our insert stack, and then our consume stack. I don't know if this is right how I'm writing this, but whatever. Actually, no. Let me look it up. Classes in C++. I just need a reminder. Yeah, so you're just gonna declare stuff, and then in the constructor I'll initialize it. I don't know if I need to initialize it or if it'll like initialize itself empty. Maybe it'll initialize itself empty. I don't think I need a. Yeah, I don't think I need to like initialize someone new. I think it should be fine. Okay, so when we're pushing, we're just gonna push in the insert stack every time. Every time we're just gonna push to the insert stack. So where we're pushing, we're gonna say insert stack dot push x, and that's gonna be it. Simple operation. When we're popping and peeking, let's leave that for last. And then for empty, we're gonna check if insert stack dot empty and consume stack dot empty. Then we return true, otherwise we return false. So we basically return that. Now in peek and pop, we're gonna need like an additional operation to like a helper, and that's gonna be reverse, like a reverse stack operation. So void reverse stack. Let's put this in private just to properly do object-oriented OOP. So here we're gonna say it's gonna be called reverse stack, void reverse stack, and we don't need to receive anything. And what we're gonna do is while insert stack dot empty, this is not true, well insert stack is not empty. Then we're going to say consume stack dot push insert stack dot top. As it should be top. Yeah, I think it should be top. This is not. Yep. We push the top of the insert stack to the consume stack, and we pop the top of the insert stack. So this is our reverse stack operation. And then up here in pop and peek, we're gonna check if consume stack, if our consume stack is empty. Let's double check. It says that, I mean, I hope that all of the operations that they give me are valid operations, so they don't try to like pop from the stack if there's nothing on it. Otherwise, they're just gonna receive an error, and I feel like that's expected. So if our consume stack is empty, then we reverse the stack. And then here we do, we need a temp here. Yeah, we need a temp. So we're gonna say int temp equals our consume stack dot top, and we consume stack dot top, and we return our temp. And same with this, but instead, actually, yeah, we have to do it this way. Here it's the same, instead of we just don't pop. Yeah, I think that this is basically what we just did in the paint example. So let's try it out. Right there. I don't know if my actual like declarations are correct, but I need to log in. Okay. I feel like I've solved this before, haven't I? I have not in this account. Okay. Fair enough. Expected after return statement. Okay, let's fix that. yeah, it passes the test, and easy. Easy, very, very, very simple. You just have to think like this. I've solved these problems before, so I remember the solutions for most of them. But I have like by doing these problems, you build the experience so that you can start thinking about them. And the implementation for this problem is like crazy easy. The only like hard part to it is thinking about how a stack relates to a queue and vice versa. So the key here is to find out the fact that um, first that it doesn't matter how you store the information, it just matters how you retrieve it and that you retrieve the correct thing. And second, that the order of a stack is the reverse order of a queue. And how you can find this out is just by doing examples, like what we were doing before. So we were seeing like, oh, okay, with a queue, this is how it happens. Let's see what would happen if I insert the elements into a stack. In which order do I have them? And what operations do I need to do to be able to get them in the same order that I would get in a queue? So you just need to run through examples, and eventually you topple into that fact, and that helps you build your solution. Then another thing that helps, and like we're gonna double check the solutions to make sure I did it like optimally. But you check for optimization. So you check what your most expensive operations are, and what can you do to minimize the expense in like time and operations that you're gonna need to have to be able to solve that operation. So if you don't need to do that operation as often, and normally this happens with a lot of data structure, and it's called like lazy loading. I mean, for this, I don't think it's called lazy loading, but like you would go into like segment trees and like other more complexity structures where you have the same problem of like, oh, doing the operation to be like, for example, to balance a tree or to like update some like this is especially happening in trees. I remember a lot. When you need to update all of the children and stuff like that, sometimes you can do it lazily, and like what that means is you don't do it every time. You don't do it every time. Like you don't have to have the perfect state every time. You just need to have the perfect state when you're accessing information. And as long as you can get that perfect state somewhere later down the road, you don't have to commit that operation immediately. You can wait until you need to access that information to actually perform the operation. But yeah, that might have been a little bit confusing, but it is what it is. I'm gonna, I have time. I'm gonna just write down like my explanation for it here. So, idea. Or actually, let's put here 2 core principles. I don't want to say principles. 2 core ideas in the solution. 1. It doesn't matter how we store the information, just that we retrieve it in the correct order. 2. 2 is that the order in which we store or we retrieve elements in a stack is the reverse of what we do in a queue. With this, we can design the following solution. Have a stack to insert the elements and a stack to consume, which in this case means pop or peek the elements. When we need to consume an element, we have to reverse the order. We have to reverse the order of the elements in the stack. We do this by emptying a stack into the other. by emptying the insert stack into the consume stack. And then here, optimization, we don't need to reverse the order again to be able to insert. We can just keep consuming from the insert stack, from the consume stack, until it's empty, and then reverse the stack. We can just keep consuming from the consume stack until it's empty, and then reverse the insert stack when we need to. When we need to. Yeah. Okay, let's double check the solutions that are here. So, oh, this is an open editorial. 2 stacks, push of and pop of 1. So here what it does is it step 1, so you insert here and then you empty, then you insert here, then you empty it back. Oh, I see. This was another possible solution, but like once again, it's just expensive to like shift from one to the other and back and to the other and back. Like, yeah, from the pop, you just pop from the top of whichever one. And then here they do what we did, I'm pretty sure. Front equals X. The newly arrived element is always added on top of the stack, and the first element is kept as front. Maybe I did it a little bit differently. Yeah, they might have done it a little bit differently here. So what's the idea here? The newly arrived element is always added on top of the stack, and the first element is kept as the front queue element. So we keep this as front, I guess. So if it's empty, we keep the front as X. Then when we pop, we have to remember the element in the front of the queue. This is the first element in the stack. It's positioned from the bottom of the stack because of the policy. Pop all elements from S1 and push them onto an additional stack S2, which helps us store the elements of S1 in reverse order. You can simply pop it from stack S2. Once S2 is empty, the algorithm transfers. Oh no, I think it's the same solution. So if it's empty, then we do the reverse of the stack right here. And I think it's the same with peak. I don't see the operation for peak, but okay. If S2 is not empty, we peek from it, otherwise we return the front. So this is okay. I think they just have like a little optimization here, which is to keep the front element. Because they only need to update it on a pop, so we're always gonna have the front element here. Yeah. Okay. Okay, yeah, that makes sense. I just have like one little optimization here for the peak, but otherwise it's the same. Because for peak, we also had to do like the whole emptying. So in this case, if they do peak, they don't have to empty it. They just get the top from like the value they calculated. Whereas we emptied it for both for peak and for pop. But it's a pretty similar solution. They just have like one little optimization there. Okay, let's check first bad version. I also haven't solved this one. That's crazy. Okay. Okay, 278, first bad version. You are a product manager and currently leading a team to develop a new product. Unfortunately, the latest version of your product fails the quality check. Since each version is developed based on the previous version, all the versions after a bad version are also bad. Suppose you have n versions and you want to find out the first bad one, which causes all the following ones to be bad. You're giving an API, is bad version, returns whether version is bad. Implement a function to find the first bad version. You should minimize the number of calls to the API. I think we can do some binary search here. So we're returning the first bad version. Yeah, so I think we're just doing some binary search. Well, in this case, we're not searching, but we are searching. We're searching the first index that is bad. And how can we minimize it? This is 2 to the 31 minus 1. So it would be 31 operations. Yeah, this is pretty. It's just a log n solution. Where do we have binary search? It's probably an array, isn't it? Binary search is number 704. 704, yeah, it's an array. So I'm probably gonna put this in array too. Let's do that. So here, first bad version is problem 278. Okay. Right. And so how are we gonna use binary search to solve this? I mean, it seems it's pretty evident. This problem's not too hard. But remember once again that computers, like if we saw this problem as a human and we saw like, let's say G is good and B is bad, if we saw like G, 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 B, 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 like it's pretty evident to us that like we can see the whole array and we can see it here. But remember that a computer cannot see all of these at once. It has to check them one by one. So you have to figure out a smart way to check this so that you minimize the amount of times you have to like check each of the indexes, each of the letters. So the first one you may come up with, the simplest one, is just going from left to right, or from right to left, and finding the first, or in the other case the last B. And when you find it, that means that is the first bad version. But if the first bad version is at the last index, then you have to like basically check the whole array. Or if you're doing the reverse, if the first bad version is at the first index, then you have to check the whole array anyway. So a smart way to check this would be check the middle. If it's bad, then in this case it's good. So if it's good, we're gonna check to the right. So we're gonna reduce our window. So before, our window used to be the whole array. Now we know that all of the good versions, all of the versions before this are good, because we know that whenever there's a bad version, all of the following versions are bad. So if there was a bad version before, all of these would be bad. But since this one's good, we know that all of the ones before are good. So this one's good. So we reduce our window that we have to search to this, and we check the middle. In this case, the middle would be this. It's a B, so we're gonna reduce our window to this plus our left. because we know that like either this is the first bad element or it's some element after. So the first bad elements are gonna be this index or some index before. So we don't have to check the ones after because we know that all of those are gonna be bad and we're earlier, so that's not gonna be the first bad version. So we reduce our window to here, and then we get our middle, which in this case would be this, and we see that it's bad, and so we can reduce our window to just this. And since we only have one element, we know that that is the first bad version. So if we find a good element, we reduce our window to the right. If we find a bad element, we reduce our window to the left, including the element we're on, because that element we're on could be the first bad version. Okay. So it's just gonna be like a regular binary search. So let's do it. Let me just first fix this. Yep. So we're gonna have an int L and a right, and our left is gonna be equal to 0. Our right is gonna be equal to n. I think n is, what's n? Is n the number of versions? Yeah, n is the number of versions. So our r is gonna be n. And actually, let's make it n minus 1 because the array goes from 0 to n minus 1. Actually, we have versions 1 to n, so it's one index, not. So it would be like this. Now, while L is less than R. Yeah, while L is less than R. Then we get our middle value. Our middle value is going to be L plus R over 2. Is this going to create overflow? 2 to the 32. 2 to the 31. This should fit in a 32-bit integer. So I think it should be fine. What's max number you can fit in a 32-bit integer? Yeah, it's 2 to the 31 minus 1. So yeah, this is gonna fit in an int. Not necessarily, actually. Because if the L is like in the middle, then it's gonna overflow. So we need to calculate this in a way that it's not gonna overflow, or we just use a long. But I don't know if a long is gonna be enough. There's a way, I don't remember how it is. So how to calculate the middle of binary search without overflow. It's this way. Okay. Oh yeah, that makes sense. So yeah. So we just do, instead of doing left plus right over 2, we do L plus right, and I'm just gonna do this. I know because of the order of operations it's gonna work out the same way, but I just like doing it this way instead. It's just like more clear. So you do the left plus the distance between the two over 2. Yep. That's the same because, I mean, let's see if it simplifies to the same. We have L plus R over 2. This is the same, is it the same as L over 2 plus R over 2? I believe. If you do 2 times A plus B is 2A plus 2B. Yeah, so yeah, it's L over 2 plus R over 2. What is this one we have? L plus R minus L over 2. This is the same as L plus R over 2 minus L over 2, which is the same, once you like simplify this, it's the same as you get L minus L over 2 plus R over 2, and that is the same as L over 2 plus R over 2. So yeah, it simplifies to the same thing. Okay, so we get the mid, and this way it doesn't overflow, because we're not calculating L plus R, we're just calculating L, and then R minus L. And we calculate the middle value, right? And then we check it. So if is that version of version mid, then what do we do? So if it is a bad version, our R is gonna become our mid, including our mid, because the version that we found could be the first bad version. Otherwise, our left version, our left is gonna be equal to mid plus 1, because left is good. It couldn't be the first bad version, but the next one could be. The next index could be. And then here we just return L, I believe. Yeah, if you're just adding them by 1, there is no way that it would like overflow. If you have 1 and 2, that's 3 divided by 2 is 1, and let's say that doesn't become, so it becomes L. So yeah, the worst case, they're just gonna become the same, so you should return L. Yeah, I think this makes sense. Let's test it out. Perfect. Let's go. Okay. Let's do a write-up for it. So the idea here is we use binary search to look for the first instance of a bad version. If our middle element is bad, then we need to check. Then all versions after it will be also bad, and they will not be the first bad version. If our middle element is good, then the first bad version is going to be somewhere in mid plus 1 to R. Yeah. I think it's pretty simple. We're still in the easy problems. Okay. Let's go back to here. We've completed first bad version. Ransom note. Okay. 383 ransom note. Given two strings, ransom note and magazine, return true if ransom note can be constructed by using the letters from magazine, and false otherwise. Each letter in magazine can only be used once in ransom note. This seems pretty simple. You have a ransom note A and our magazine. Oh, okay, so this is like anagram, like valid anagram. Where is it? Where's the anagram question? Valid anagram. It's very similar to valid anagram. The only thing here is, so in valid anagram, we checked that first of all, that both strings were the same length, and they also had the same letters in the same amounts. Right? In this one, they don't have to be the same length, and they don't have to have the same letters in the same amounts. We just care that magazine has to be a superset of Ransom Note. So a superset, just as a reminder, is so in set theory, a superset, if you have like, okay, a set is a collection of things that are unique. So we have here our set Ransom Note. We'll just call it ransom. And it's going to have a bunch of letters. Let's say it's going to have like A, it's going to have B, it's going to have C. And then we have here our magazine. Our magazine has to be a superset of ransom. So it has, ransom has to have letters that are in magazine, but magazine can have more letters than those in ransom. So magazine can also have here D, E, F. It doesn't matter as long as we can form the word in ransom with the letters in magazine. So you can think about it a little bit kind of like if you've done the New York Times, the B, what is it, NYT Games. What is the name of the B one? This one. The spelling bee. You get like 7 letters, and then you need to form words with those letters. In this case, our magazine is gonna be the 7 letters, and our ransom has to be one of the words that we can form with those seven letters. It's pretty simple. So, okay, this is gonna be a string question. Nope. And it's going to be question 383.cpp. Okay, so to do this, I'm going to count the letters in the magazine, and then I'm going to reduce them by 1. I'm going to reduce the counts by 1 every time I found a letter in Ransom Note. If at any point I find a letter in Ransom Note that has 0 count, then that means the magazine is not, you can't make a Ransom Note with the magazine. So let's go count them. How are we gonna keep the counts? Let's create a set. Do you care about log n instead of of1? I mean, we can do an ordered map. Yeah, let's do an unordered map, and it's gonna map char to an int, and this is gonna be our count. Now we're gonna go and actually count set elements. So okay, so for char C in magazine, if count.count of char C, so if char C is not already in our count, then we create it. We say count of C is going to be equal to 1. Otherwise, our count of C, we're just going to increment it by 1. Okay. So we've done the counts, and now we go over all the characters in the ransom note. And here okay, so first of all, if in our count we don't have set character C, then we return false. Because if that letter was not in the magazine, like the other one, then we have to return false. Okay. One other optimization we can do here is magazine has to be of length bigger than or equal to ransom note, always. So we can just check that at the beginning. So if magazine dot length is less than ransom note dot length, we return false. We can do that optimization at the beginning. Okay, now continuing here, if we've run out of the letter that we need, then it's also false. So if count C is less than or equal to 0, return false. Otherwise, count C minus minus, and we return true here at the end. Okay, got accepted. Nice. Why is it so slow? Let's check the solutions. Maybe... Do I need to count all the characters? Is there a smarter way to do this? Maybe I don't need an unordered map. This should be all of 1. It's 11 milliseconds. Honestly, it's not that big of a deal. Counting each character. Yeah, so from what I read here, we did it in the most optimal way. Oh, this is not an open editorial. Never mind. Yep. This uses like an array instead of an unordered map. But yeah, should be the same. I could try, maybe array operations are like optimized. They probably are. Like for CPU operations, so they actually like make it faster. But I mean, this worked. I think it should be fine. It might be just like variance. Okay, let's do a write-up. Similar to what's valid anagram. 242 valid anagram. We count the letters in ransom note and magazine. Magazine has to be a superset of ransom note. Okay, in valid anagram, we had to check at the end that we had used. I mean, okay, we can say we had to check that both strings were the same length, but in this problem, magazine can have more letters. I think that explanation is probably sufficient. Okay. What's next? Ransom note is done. Climbing stairs. I've solved this problem. I haven't solved it on stream. Should I solve it on stream? Or should I just move on to longest palindrome? I think we're getting onto harder stuff, but still pretty simple. When's the first medium? In week 4. Damn. Do we just do all easies, then all mediums, then all hards? That is crazy. Why is it ordered by difficulty? I should have put it in all rounded. What am I doing? I'm gonna be doing easies for like the longest time ever. Climbing stairs. Yeah, the thing is, it's probably fine. Okay, let's do all rounded. Ooh, insert interval. I remember this. Okay, we're gonna start doing some mediums. I see how it is. Actually, I haven't solved. Have I solved maximum subarray? I haven't solved maximum subarray live, have I? We can find out pretty easy. No, because this is DP. I don't think I've solved DP live. Definitely not. Okay, I'm just, so this is practice for me. And like, I'm honestly not I posted some solutions to LeetCode problems, but I'm not going to be posting all of them, I don't think. I don't want to become a LeetCode channel. We're just going to go with like what I think it's the best practice for me. And what I think that is doing all rounded. Let's do all rounded. We're going to be doing a lot of mediums, but that's probably good. I need the practice in mediums, and I'm going to start messing up more probably. But this is very good practice. Okay, 57. Insert interval. You are giving an array of non-overlapping intervals where intervals I, start, end, represent the start and end of the ith interval, and intervals is sorted in ascending order from start. You are also giving a new interval that represents the start and end of another interval. Insert new interval into intervals such that intervals is still sorted in ascending order by start, and interval still does not have any overlapping intervals. Okay, this is very complicated wording. Return intervals after the insertion. You know that you don't need to modify intervals in place. You can make a new array and return it. Okay. So here, in this example, we have an interval 1 to 3 and 6 to 9, and we insert 2 to 5. So that means that 1 to 3 becomes 1 to 5, and 6 to 9 stays the same. That is obvious. I mean, let's illustrate it here. So let's say we have our number line, and we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So at the beginning, we have two intervals. We have 1 to 3, and we have 6 to 9. 6 to 9. And we insert 2 to 5. We insert an interval here. So we have to merge these intervals. So this 1 to 3 becomes 2 to 5. Yeah, I think this is pretty simple. I think there's just when you're thinking about it, like you have to think about how you're gonna do it. But otherwise it's pretty simple. I think there's a follow-up question. Yeah, there's merge intervals. This is just insert interval. Merge intervals it's a lot like this one, but it's a little bit harder. Okay. So let's do the next example. You have 1, 2, 3, not 6, 4, 5, 6, 7, 8, 9. So you have interval 1 to 2. You have interval 3 to 5. You have interval 6 to 7. You have interval 8 to 10. 10, 11, 12, We have to go to 16, 13, 14, 15, 16. You have 8 to 10. And you have 12 to 16. And now you insert a new interval 4 to 8. Now what's going to happen here is, if you see, this interval is touching these three intervals and it's connecting them together. So what you're going to do is you're going to basically merge all of those. You're going to merge all of these three intervals together, so that now you're going to have a big, like, 3 to 10 interval. Right? 3 to 10. Because there's an overlap. So you're checking for overlaps. Now, how do you check for overlaps? Let's think about that. So let's go with the example we got here, which is we insert 4 to 8. How do we know that it's overlapping? We know we have here 4 to 8. So we know that these intervals are sorted, so we can go to them in order as if we were going through the number line. So we have 4 to 8. At each interval, we have to check, is any number in here inside this interval, including the ends? So 2 and 1 would be included. So we have, the numbers in here would be 4, 5, 6, 7, 8. None of those numbers are in the interval 1 to 2, so we can move on. Then we have interval 3 to 5. Well, we know that the number 4 is in that interval. So this interval would be included. Then the next one. Is there any overlap? Yes, number 6 and 7 are here, which overlap with this interval, so we include it as well. Then next, are these numbers included in that interval? Yes, 8 is included in that interval, so we include it as well. And now another thing we need to keep. When I say we're keeping these intervals, what are we doing with them? It's basically we're gonna replace them. These are gonna be merged. We know that these three intervals are gonna be merged with the interval we're inserting. Now, to merge them, we have to keep track of two things: the beginning and the end. So the beginning is gonna be the minimum number out of the first interval we find and our interval that we're inserting. So in this case, like the beginning is 3, but you could have it like an interval like right here, where it's like, I don't know, 2.5 to 3. In which case the beginning of the interval will be 2.5, not 3, because it starts first. So you need to keep the minimum between the first interval you encounter that you need to merge and the interval you're inserting. And the last interval is going to be the maximum between the interval you're inserting and the last interval you need to merge. And the right end of the last interval you need to merge. And the problem already tells us that we can create a new interval to return, so we don't have to work with the interval that we're given. So what we're going to do is go from left to right. If the interval does not need to be merged with the inserted interval, we can just put it in, and we create a new interval that we're going to return. If the interval we're checking right now doesn't overlap with the interval we're inserting, we just insert it as normal. We put it in the new interval. If it does, then we keep consuming intervals that we need to merge, and at the end we just insert the merged interval. We keep the left and the right, and at the end we insert an interval that is from left to right. And then after that, it's just going to be the same as all the other intervals. Okay? So we have 3 steps, basically. The beginning, any intervals before the interval we're inserting, then any intervals we're merging, and then any intervals after. But it's pretty simple. What kind of questions is this? Probably like an array question? Yeah, okay, let's put in an array. 57. Maybe I should. Yeah, make it a little bit bigger. Okay. Oh, so let's do this. New int. Oh, this is new interval is the interval we're inserting, right? Okay. Let's keep it as L and R. I don't like keeping this new interval, so we're just create a new, like, L is going to be equal to new interval 0, and R is going to be equal to new interval 1. That way we just keep L and R, which is going to be the left and the right index of the interval we're going to insert. It's just going to be easier for axis. Now, for each interval in intervals, I'm just going to do auto interval in intervals. What are we going to do? Well, we're gonna create like a I'm also just for like easiness, we're gonna create a cur L and cur R. Yeah, I think we can do this. Cur L and cur R, and cur L is gonna be equal to interval 0, and cur R is gonna be equal to interval 1. Now, how do we check for the overlap? I didn't actually show this here, but if there's two cases of overlap, right? Either the left part of the interval is in between these two numbers, or the right part of the interval is in between these two numbers, or there's another case in which the interval is bigger than both numbers. So like this interval is a subset of the bigger interval. Is there any other case? Yeah, so either it's one of the edges is inside, or it's just contains the whole interval. And how do we check for that? So I think this is the hard part of the problem, how to think about checking the intervals. Like I could do those three things, but I think there might be like I mean, let's do it first the dumb slow way, and then we'll do the complicated way. So there's three conditions in my dumb slow way. First, we're gonna call this cur L, cur R, and this is gonna be L and R. So the first condition is cur L less than L less than cur R. Actually, this should be less than or equal. Cur L less than or equal to L less than or equal to cur R. The other case is cur L less than or equal to R less than or equal to cur R. The last case is L less than or equal to cur L and cur R less than or equal to R. Those are our three cases. How do we simplify them? Can we simplify them, or do we have to just check all three? So when I think I'm just gonna do all three checks. It just works better for me. Like I can think of it that way a little bit easier. So actually, let's create a function called overlaps, and that's gonna make our life easier. So bool overlaps, and then we're given cur L, cur R, we're checking. I'm just gonna keep the naming the same, and then int L, int R. So if cur L is less than or equal to L, and cur R and L is less than or equal to cur R, return true. If cur L is less than or equal, actually let me do the braces. Cur L is less than or equal to R, and cur and R is less than or equal to cur R, then we return true. If L is less than or equal to cur L, and we know that cur L is less than or equal to cur R, and cur R is less than or equal to R, we return true. Oh, I'm missing the semicolons here, that's why it didn't work. Okay. Otherwise, we return false. And actually, we can simplify this whole condition in this way. We're just gonna return that, or that, or that. Otherwise, false. So if not overlaps, actually we need to create our new interval that we're returning. So vector of int, we're gonna call it ans for answer, and it's gonna be, we're not gonna give it a length yet. Oh, now I'm thinking, I can. So if it doesn't overlap, we're just ans dot pushback the current interval. I think that works pretty well. Actually, that'll be a copy. I hope this works. If not, I'll just copy it over and then actually do it, because it's a reference. Maybe it'll work. I don't know. Because it's a pointer. I don't think it's gonna work. Well, let's try it. So if it doesn't overlap, just push it back. Otherwise, right here, else RL is gonna be the minimum between both. L is gonna be the minimum between L and per L, and our R is gonna be the maximum between R and cur R. And then another thing we need to keep track of here is if it doesn't overlap and the L is after, we need to insert the interval we found. So if our cur R is bigger than R, then let's create a vector of int new interval. I also don't think this is gonna work either, but let's try it. Or actually, I think I might be able to just create it on the spot. So just do ans dot push back LR. I think I can do that. And then here an interval, so I don't have the same problem. I'm just gonna do ans dot push back cur L cur R. and then we return ants. I think that syntax should work for vectors as far as I remember. So what we're doing here is, if the interval overlaps, we just update our LNR and don't insert the interval. If it doesn't overlap, just insert the interval. And then once we're past our interval that we're inserting, we insert that interval we're inserting that should have its LNR updated, and then we can insert the non-overlapping interval. So what that means basically is, we insert non-overlapping intervals before. Then any overlapping intervals we don't insert, we just update our LNR. That is going to be the big interval that we're going to insert at the end. And then once we know we're past the interval, we insert that big overlapping interval. Another check we need to do here is, if the overlapping interval is the last one, this is not going to trigger. So how do we fix that? I'm just going to create like a bool has inserted equals false. We just, here we make it has inserted equals true. And then at the end, if not has inserted, then ans.push back LR. Yeah, that was like the last edge case there. Let's see if I didn't make a mistake. Oh, I need to actually call the function. That's right. If not overlaps per L per R, L R. I feel like I don't know, it might be because I'm doing it like in front of an audience, but I feel like I'm writing better code. Because before, I probably would have written this whole like big ass function inside here, and that wouldn't have been as readable. But now, because I feel like I'm having to because I try to explain what I'm doing, I do it in a way that if somebody else read it, it would be more understandable. Because a lot of the times, I think one of the issues that I have is that when I'm writing code, I only think about myself. So I'm like, oh, if I read this in the future, I'm going to be able to understand it because I wrote it. It might be a little bit complicated, but like it's fine. It's the same. It does the same thing. So why bother refactoring it in a way that's easier to understand if I can understand it? But when I'm in this process of like explaining my approach to you guys, I think more about how I can make the code as simple as possible, so that if when you are reading it while I'm writing the code, or whenever I push it and somebody reviews it, it's going to be easier for them to understand. So I think actually doing this exercise of like talking through my approach makes me, I don't know, I feel like it makes me a better programmer. It makes me like write better code. Anyway, I think this is probably gonna pass. And also, I think a lot about wrong answer. Okay, we'll check that in a second. I think a lot about edge cases when I'm doing it, because I'm talking through the approach wholly. Because a lot of times when I'm practicing these by myself, I'm like, okay, it seems to work for like the edge cases I can think about, and I just get lazy and I'm like, oh, I'll send it in and then if it doesn't work, I'll fix it. Whereas here, when I'm talking through my approach, I figure out a lot of like edge cases that that I wouldn't have necessarily if I was just doing it by myself, just lazily. So I think this is a good exercise. Problem here. So insert 0 to 1. Oh, I didn't think about, look at me talking about edge cases. I didn't think about one edge case. So here are not overlaps. We're only caring about two things. We have this edge case right here, which is the inserted interval is going to be the last one inserted. We have this edge case right here, which is the inserted interval is in the middle. We're missing one edge case. What if the inserted interval is the first one? That's the one we need to handle. So we need another thing here. Actually, I'm just gonna write another condition here. if cur R is bigger than R, or actually let me write it the other way around so it's L to R. So if cur L is bigger than L, no, wait, sorry. Cur L is gonna be the interval of the one I'm checking. So if cur L is bigger than R, or does that make sense? Why is it both bigger then? If cur R is bigger than R. Oh, I think this is the wrong answer. It's if cur L is bigger than R. Because we know they don't overlap. So if cur L is bigger than R, or our cur L is bigger than R. That doesn't... Okay, let me draw it. Let me get rid of all of this. So, two cases. We have this case, in which my R is smaller than cur L. And then, in this case, let's switch it. Let's do the other case, in which my cur L is bigger than R. In this case, R is smaller than cur L, or R is bigger than cur L. Yeah. R is bigger than cur L, or... What does that tell me? I don't think this is right. Because okay, so basically if it doesn't overlap, we just insert it? No. So this is just basically saying if curl is not R, if curl is equal to R. This doesn't make sense to me. I must be doing something wrong. Let me go through it again. So if we have our L and R here, and our cur L, we're going through it in order. Our cur L is bigger than R, and we know it's not overlapping. I mean, if it's bigger than R, then it's not overlapping for sure. Then we have to insert cur L. Oh no, we have to insert the interval. We have to insert the interval and then insert the current interval. Here, if our R is smaller Wait, I'm doing the same example twice. Huh. Yeah, because we're going through them in order. What did I submit? Cur R is bigger than R. Yeah, I think I just need to do it like this way. If cur L is bigger than R, we insert. I think it was just because I had the wrong condition. Maybe this will work now. Use test case. No. Oh, we also have to check if we have inserted it. And not has inserted. Yeah. Because before we inserted it in between anyone after. Yeah. And we just need to insert it the first time it's after. Okay. Submit. Let's go. Insert interval, done. Doing some mediums, let's go. 0, 1 matrix. Okay. Given an m by n binary matrix, return the distance of the nearest zero for each cell. The distance between two cells sharing a common edge is 1. So the output here is going to be 1 for this one and 0 for all of the other ones. And this one is going to be 1 for each of the other ones. Actually, it's going to be 2 here. I think this is going to be some sort of propagation. Yeah, I think I know what I think I know. So, okay, I'll just explain the problem. So here, you're trying to find for each of these cells, what's the minimum distance between them and a 0. So if the cell is 0, the minimum distance between itself and a 0 is 0, because it's already at 0. But if it's a 1, the minimum distance is the shortest path from that cell to a 0. So in this case, it's 1, because you go from here to here, there's a 0, or here to here, or here to here. You can only travel to adjacent, so up, down, left, or right, not diagonals. With this one, this is the nearest 0. With this one, this is the nearest 0. With this one, you have a distance of 2, because you have to go either up here or here. Yep. Now one fact here is that we can use the distance from the nearest okay, let me think. We can use the distance from all of our adjacents to figure out what the distance is to the nearest 0, right? So for this one, if we have an adjacent 0, then the distance is 1, because whenever it's a 1. For a 1, if it's surrounded by 1s, then the distance is going to be the minimum distance between all of its adjacents plus 1. Now here there's a problem, and it's what order should you do, the order in which you should fill in the distances. Because if you fill it in here first, you're not going to have the distances for these 3. So you need like a topological sort. And what that means is we're going to start with all the zeros and update those distances to 0. And then for all of the ones that are adjacent to a 0, we're going to update it to 1. And then we're going to go into the next depth and the next depth and the next depth. So we're going to go from outside to inside. If we go from inside to outside, we're not going to have the values to outside. Okay? So actually, we could use the matrix that we're given and then explore it. It's 10 to the 4 by 10. They're both 10 to the 4, so we're not going to be able to explore the whole matrix. If m and n are 10 to the 4? Wait. Oh, okay. So we're given this constraint. Never mind. So we are going to be able to go through the whole matrix. We need to do some sort of topological sort. So we start at zeros, and to each adjacent 1, we update the distance to 1. And for each of those, we update the next distance to 2, and the next distance to, okay. Okay. I think we can do this programmatically with a queue. Actually, let me write the solution for this. Okay. So the idea here in the previous one was insert any non-overlapping intervals. Then for any overlapping intervals, merge them with the inserting interval, and then insert the new interval, then the merged interval. Not the inserting, I guess, with the new interval. So merge them with the new interval and then insert the merged interval. 3 cases to check for overlap. 1. The left end of the new interval is inside the current interval. 2, the right end of the new interval is inside the current interval. 3, the cur interval is wholly. Is that how you spell wholly? Or is it double 2 L's? I think it's 2 L's. Yeah. I mean, I could just say entirely, I guess. It's entirely contained by the new interval. To find merged interval, keep the minimum end of all overlapping intervals and the maximum end of all overlapping intervals. The merged interval should be min L, min R. Yeah, and there's some like implementation details and whatnot, but this is the like main idea. Like some implementation details, like this has inserted value, and then this check at the end, but otherwise it's pretty much just as I've explained there. Okay, now we're doing, this is like a matrix question. This is like a traversal question. What's same as 1765 map of highest peak? Dynamic programming, breadth research, matrix. Where do we want to put this? I mean, it is kind of a DP question. I mean, let's see where this puts it. What's it called? 0-1 matrix? Graph. It is kind of a graph problem because you're doing a traversal basically. Okay. You're doing a traverse. Oh, lead code goat, thanks. So let's put it in graph. I'm gonna create a new folder for graph because I don't think I have one. Graph, and then graph slash, what is it? 542.cpp. I mean, it says this is the same solution as 1765. Should I put that there? I'm just gonna put here 542 or 1765. You know what? When you read the question, it tells you that it's the same. So, yeah, whatever. Okay, graph that. Okay. So we're gonna do. I'm gonna do a BFS. Yeah, it would be a BFS. You can do it. I think you could probably do it in a DFS way, but I like BFS better. Okay. So we don't need to update. We don't need to create a new matrix. We can just use the one we're given, and then just update the values. Yeah, I think that's what's probably best. Okay. We have to start at a 0, so we find the first 0 that we can find. Actually, we have to expand at every possible 0, because there could be multiple islands. So we have our matrix here. It could be like a very big matrix. And we could have here like multiple islands. You could have like an island here, and like one island here. So if we start here at the 0, we might only like check this island and skip it, so we need to start at every possible 0 to find all the different islands. Okay, so how do we do this? Okay, I just add every single 0 to this. We're gonna have a queue because we're doing a BFS. And then in that queue, we're going to have the position. So I'm going to create a pair int. That's going to be our queue. And do we put all of those positions in the queue? All of the 0s in the queue. Okay. Because we're gonna have to check them in order. Now I'm thinking, because you need to check all the ones around them. Maybe I'll add, this will be like actually like a vector instead, because I'm gonna keep 3 things. I'm gonna keep the position of the x index, the y index, and then I'm gonna keep the distance that I should put in that index. How do we do this? Okay, let me think. Let's write out. So let's say these are all 0s. What happens if we do a regular BFS, as I was gonna do at the beginning? I think that would probably work, but I need to see it. So we have a queue, and we add all of the 0s to the queue. So we would add this position, this position, this position. And for all of those 0s, we basically do nothing because we already got the correct distance. So we just visit them, and that's it. And then we add them to a set. So we're not visiting the same ones over and over. Then, for each of these, we add any adjacent positions that we haven't visited. So here we would have added all 0s. For this one, it's not going to add this one because we would have added it at the beginning to the set. Oops. But then for any 0s that are adjacent to a 1, we're gonna add that. We're gonna add those 1s. And for those 1s, it's gonna check the 0 next to it. So let's see which 0s we would visit first. Which ones we would visit first. We would visit this one, 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 and this one. So once we visit all of those, we know that distance is 1. We also don't do anything with these, but it's important that we go from out to in. So we have to do this process anyway. Once we go through all of those, these ones are going to get added. Right? And so once these ones are added, then we know we've calculated all of the minimum distance of its neighbors. Which should be 1. But okay, so maybe I can't use the original matrix. Because I think I need to create a new matrix. So we're gonna create a vector of int, and this is gonna be our answer matrix. It's gonna have mat.size elements, and it's gonna be initialized with a vector of int of size mat0.size, and we're gonna initialize it with infinity. Yeah, let's initialize it with infinity because we're trying to calculate the minimum distance. Okay. And so now that we've initialized all of those, okay, now we can actually do the process that I was talking about, which is visit each of these indexes. So we visit all zeros first, and then we update the distance on the matrix, and then we visit all of the ones that are close to zeros, then all of the ones that are adjacent to that, so we visit them in order. Okay. I feel like we could do probably like a DFS in like some sort of smart way, but I like BFS better. I don't know why. No, BFS makes more sense because you know you're gonna reach the minimum distance in order. You're not gonna have to like update it over and over and over. So here, we're gonna iterate over the entire matrix. For int I equals 0, I less than mat.size. Actually, we'll say int n is gonna equal to mat.size, and m is gonna be equal to mat0.size. And here on mat.size, we're gonna say n instead, and mat0.size, we're gonna say m. So I less than n, I plus plus. Then for int o equals 0, o less than m, o plus plus. If mat io equals 0, then we push that to the queue. Queue that push back io. Is this easier than writing first? I like pairs better, so we'll create a pair. Int. Queue that push back io. Okay, now that we've pushed all of those while the queue is not empty, there's always going to be a 0, I hope. There's at least 1 0. Okay, because if there's no 0, then the distance would be maximum each time. So while our queue is not empty, we're going to pop whatever's at the front. So we're going to say cur x, cur y is going to be, cur x is going to be equal to, actually, cur is going to be equal to q.front, and then q.pop, and then int cur x, cur y is going to be equal to cur.second, cur.x is going to be equal to cur.first, and now we can go to work. So if we're a 0, then the distance is 0. So if mat cur x, cur y is a 0, then our ans cur x, cur y is also 0. Then we also need our set of the elements we visited so far. So we'll create the set here. Set of pair int st. And every time we push back here, we do set.insert io. So we pop from the front. We check if our distance is 0, then the distance, if the current element is 0, then our distance is going to be a 0. Otherwise, we're going to check all adjacents and find the minimum. I'm going to make that as a different function. So we're going to say int min adjacent, and then we're going to receive the matrix. Yeah, we're going to receive the matrix. And a position, int per x or int xy. So int min dist is going to be equal to int max. If okay, so if no, we should check them in order. So if our actually, let me copy this. Okay. If x minus 1 is less than 0, actually if x minus 1 is bigger than or equal to 0, then min dist equals min of min dist and mat io. If y minus 1 is bigger than or equal to 0, it's not io, it would be x minus 1 y. Here it's x y minus 1. If x is less than n, min dist equals, actually it's x plus 1. Min of min dist and mat x plus 1 y. And then down here, if y plus 1 is less than m, then we do the same, but y plus 1. And then after all that, we return our minimum distance. And right here, so we're gonna get the minimum distance of all my adjacents. So otherwise here, else ans cur x cur y is going to be equal to min adjacent of my answer matrix and cur x and cur y. Okay. And now that we've updated the distance of the current one, then what we need to do is update, now check all the adjacent ones and add them to the queue. So it's going to be similar to this kind of. But instead of x minus 1, we're going to say cur x. It's going to be something like the period minus 1. Cur y. And then period plus 1 for x. And then cur y. But inside, so So here, if curx minus 1 is bigger than or equal to 0, and not st.count cur x minus 1 cur y, then maybe I don't need that. q.push cur x minus 1 cur y. Then we also need to add, or actually yf that. And And now we just update these right here. Plus, actually, cur x plus 1. This shouldn't be, this should be cur x, cur y minus 1. And cur x, cur y plus 1. So we do all of the adjacents. And then we update them here. You have to be so careful doing these problems because you can mess up very easily checking all the adjacents. X minus 1, y minus 1, y plus 1, x plus 1, y plus 1. We push all of the adjacents as long as we haven't visited them. X minus 1, y minus 1, x plus 1, y plus 1. And then at the end, we return our ants. Let's see. No pushback in queue. Yeah. I thought I did that. Cannot use dot separator on a type. Ah. No viable conversion from value type to int. Oh, yeah. Right here, this should be a pair of int. Let's see how many more syntax errors I made. Okay. Right here, I need to add semicolons to all of these. Do I have semicolons for these? Not for all of them. It's like I don't even know how to code. Infinite loop? Yeah. Oh, I'm missing st.insert. I mean, whenever we visit them... No, not when we visit them. We have to do it when we add them. Ugh, this is gonna be a dumb edit. It's when we add them, because otherwise we're just like gonna do a lot of repeated work. st.insert should I do a macro for this? Let's do a macro. So QA, recording A, and now we do st.insert. Do that, and then we go up, y inside bet, go down, we f that and paste, Then we press Q again. And now we look up Q. A. That seemed to work. Okay, yeah, that worked. I love macros. It's like pressing period, but with extra steps. Oh. Right, we get the minimum adjacent plus 1. That's the fun part. Nice. Let's go. Very slow. Yeah, I feel like if I'm not doing it in the correct way. It works. Okay, let's submit it again. Might be much faster. Yeah, no. I think there's a few optimizations you can do to this. For one, I don't think you need to add all the zeros. So when we do this loop right here, when you find the zeros, you can just update the distance. You don't need to push that into the queue. Because we're doing it twice, basically, for every zero. We're visiting them here, and then we're going into this queue anyway. So maybe we just insert all of the ones that have adjacent zeros. And that way we skip doing this twice. Maybe that'll help. Okay, so we're just gonna do here ans I O is gonna be equal to 0. We can just do that right away. And then we can put them in here as well. And else if we're gonna say adjacent 1. It's gonna be adjacent 0. And you're gonna receive the matrix and position IO. Then if you have an adjacent 0, then we put it in the queue. Q.pushback IO and st.insert IO. Okay. Adjacent 0 mat IO, Q pushback, STL insert. And now we have to create that adjacent 0 function, which is going to be very similar to this min adjacent. Instead, adjacent 0. You receive a matrix, x, y. If x minus 1 is bigger than or equal to 0, and mat x minus 1 y equals 0, then return true, otherwise return false. So we're gonna have all these conditions, and mat x y minus 1 equals 0, and mat x plus 1 y equals 0, and mat x y plus 1 equals 0, and we can just do this, return, maybe do it the other way around. Okay. Return. We don't need that anymore. That. Or that. Or that. Or that. Or that. Maybe this is better. So here we're only pushing ones that have adjacent zeros. So let's see. This should be a small optimization. No member pushback in queue. I know. Okay, maybe that improves it. I went to 103. That's better. $110. Okay, so it improved it, not by much. It's just a lot of checks. I think, what if you do DFS? If you do DFS starting from 0, what if you do DFS, actually you do the DFS from 1, from every 1 inside the data set. And then if you already calculated the distance for any point, you just return it. Otherwise, return the distance, the minimum distance between all of its adjacent ones minus 1. That is another solution. Maybe faster. Maybe. I could do it. This already works. I mean, I'll just illustrate the example with DFS. Actually, maybe I shouldn't do this. Let's remove all these circles. So you would check over every one, and then explore, do a deep first search to find a 0. When you find a 0, you know the distance for that. Otherwise, the minimum distance for this is the minimum distance. Actually, okay. So if I get to a 0, my distance is 0. That's my base case. In any other case, my distance for here is the minimum distance between this, 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 and this plus 1. So I start at all ones. I started all. Yeah, I just have to go over like everything. And just keep like a memory. Do I want to program this? I feel like that sounds cool. And we'll see. I'm actually interested about like the performance. So we'll call this. Okay, let's go back here. Is it R? Not R. R like that. Yeah, moving. So we're gonna call it 542 BFS. this is gonna be my 542 BFS.cpp. And now we're gonna create a 542 DFS.cpp. Let's copy the solution. So update matrix. We don't have a queue. We do have an answer vector. We do have a set. But this set I feel like should be here. It's a global set. It should like persist in between calls. Actually, we could even like just put it outside. You know what? Leave it here. So we have our ands. We do iterate over all of these. And we don't need this. We don't need this. We just need int DFS. And it's gonna get the matrix. And then the position. Then we have a base case. So if mat I o equals 0, then we return 0. We have another base case. If our set already contains it, if our st.count I o, then we return stio. Oh, this has to be not a set, but a hash map. It's gonna map a pair of int to a distance. We're gonna call it a hash map, not HV, hash map. If st.countIO, return stio. Otherwise, and I'm gonna have to copy a little bit from our BFS solution on this part. It's just gonna be this basically, because we're gonna find the min adjacent. So if x minus 1, then min dist is gonna be equal to DFS of our matrix. Oh, actually no, it's gonna be equal to the min dist. I can probably do this all in one. No, not necessarily, because I can't expand. Oh. Yeah, it might be. Okay, so we're just put all these conditions. So I'm gonna need to copy the other thing actually. I'm gonna need to copy nah. I'm gonna need to copy nothing. I'll just do it off of here. So if x minus 1 is bigger than or equal to 0. No. Okay. So if x minus 1 is less than 0, or y minus 1 is less than 0, or x plus 1. Oh no, it's just, sorry. If x is less than 0, or y is less than 0, or x is less than mat.size, or y is bigger, not less than mat.size, bigger than or equal. or y is bigger than or equal to mat0.size, then we return int max. That's not a valid position. That is a base case. Otherwise, we return the minimum between DFS of mat I minus 1 o, DFS of mat I o minus 1, DFS of mat I plus 1 o, and DFS of mat I o plus 1. Let's separate these. Maybe do that. Do that. And do that. I minus 1, O minus 1, I plus 1, O minus 1, O plus 1. I plus 1, O plus 1. We return the minimum distance of all of the adjacents. If that distance is not in between the grid, then int max. If we've already calculated it, then return it. If it's 0, then it's 0. Otherwise, calculate it. So for each position, return DFS. So my ans of IO is going to be equal to DFS of mat IO. And then at the end, we return ans. Maybe this will be a faster solution. Okay, let's do the DFS solution. Undeclare identifier X. Yes, because it's I and O. So X is going to be replaced by I. And Y is going to be replaced by O. Undeclared identifier ST. Yes, because it's now hash map. Hash map, I said. I expected that after a statement. Okay. Okay. Call to implicitly delete a default constructor of solution. Huh? Oh. Okay, I can't. What did I just do? Oh, I pressed FF. Q? There you go. I can put this here at the top. The only problem is, that I have to worry about is to clear it every time. hmap.clear. Every time we're called this solution. I think it's clear. Let's look up the operations. Unordered map C++. Is there a clear? Clear contents. Okay. Because otherwise this is persisted over different solutions. That whenever we call update matrix, it calls it with a different solution to fix. And so we don't want to persist the state in between calls. Okay, let's see if this works. Call to implicitly delete the default constructor of an ordered map. Oh. There's no hash for pairs. So what's the solution? I create a hash function for pairs. Use map, which works with pairs. Okay, let's use map. I don't want to create a hash function for pairs. This is just implementation details. But there's no hash function for maps. There's no hash function for pairs. So we have to use a map instead. Time limit exceeded. Oh, we're forgetting to actually insert stuff into a hash map. So hash map of IO is gonna be equal to this, and then return hmap IO. Here we also need hmap IO is gonna be equal to int max, and return hmap IO. And then here hmap IO is gonna be equal to 0 and return hmap IO. Ah! God damn it. Stack Overflow. In what order? We do this first. I less than 0, O less than 0, I bigger than or equal to max.size, O bigger than or equal to max0.size. In 17. Ah, that doesn't help. Stack Overflow and address, it's for a vector. I less than n, O less than m, my answer is of size n by m. So we want to create n vectors of m elements. Yeah, it should be nm. That should be correct. I wish this told me where I'm getting an error. Okay. Where would we be accessing? You think this mat 0? I mean, it has to be at least one, so no, that shouldn't be a problem. I'm assuming the way we initialize this... I mean, let me just look it up, how to initialize a matrix in C++. Vector of int, matrix, rows, columns. Rows, columns. If I less than 0, actually we don't need to return this. We just return int max. We don't need to save that answer. It's the same. It's gonna do this check and open anyway. If we have an answer, we return it. So this should go through. Okay, let's do cout I O N M. Actually, we don't have N and M here. Mat.size. Mat 0, not size. Am I checking 0133 1033? Why is it repeating them so much? Okay, so that's why it's reached the Stack Overflow. And I think the reason why is like, even if we've already visited that node, it keeps like, wait, no. Oh, what did I just do? Okay. Here, even if we visited that, it still calculates it. And then when it calculates... No, but what it should do is it should return here and not go back and do the FS. 0133, 0133, so it just keeps repeating the same ones over and over. Is this condition ever triggered? Cache hit. So we have some cache hits. One 033 cache hit. So it returns HMAP. Okay, well the problem here I think is if let's say we have like a big island here. If you're here, then it goes checks here, it goes checks here. Then it can't find anything here, it finds int max. Then you go check here. And then this goes checks here, returns 1. No, it doesn't return 1 because then it goes tries to check here. The minimum distance is 1. You can't have a 1 with a more like a minimum distance. What am I doing wrong? Do I not remember how to do a DFS correctly? Okay, I'm just getting an infinite loop here. What if I do a smaller... What is the example that's running in the test? It's not that big. So it shouldn't be going like back and forth, back and forth. Let me see here. We do first the cache hit, and then we check if it's 0. What test case am I getting for this? For this one. Oh, it's the second one. And I think it's because of these adjacent. Because if we just do the first one, let's say. Yeah, it gets the wrong answer, but I think it's because the second one has these like adjacent ones. It just goes back and forth, back and forth, back and forth. Why does it do back and forth? Okay, let's do this example. Let's try out the example that we're doing and let's see if we can figure it out. So this is a 3x3. And then just ignore this that I did extra. I mean, actually just do that and do that. 3x3. And then we have 0, 0, 0, 0, 0, 0, 0, 0. And 1. So let me actually just... What is this for? Resize and skew? Do that. Cut. Paste. Make smaller. Okay, we have this matrix, and then I'm going to create a similar matrix, but for... a similar matrix, but for the distances. Okay, so our program, it goes here to the first one, it puts a 0 there, and then it's done. Then it goes here, puts us, and actually this should be 1, 1, 1. Puts a 0 there, that's done. Puts a 0 here, that's done. Puts a 0 here, that's done. It gets to here. And then it tries to calculate the minimum distance. So we find a 1 here. We find distance of 1 here. Because it does, what order does it do? Left, so sorry, it does up, then left, then down, then right. Up, left, down, right. So up and left just return immediately. Then down, it needs to calculate the distance. So then it goes back up, and that hasn't been filled yet. And then it goes down and then it goes up. Okay, I see where the problem is. So what do we do in that case where we haven't filled the answer for this one yet? Maybe we keep a set of the one, no. Because here when it finds this 0, it should give the answer immediately, but I feel like we would still get in, like, if this was the first one that was checked, sorry, if this one was the first one that was checked, then it would still do the loop. Maybe not. So maybe it's just because of our base case. Let's try updating the base case. See if that helps. So here, instead of doing them all at once, we do them in order. So okay, we do hmap IO is equal to the minimum of hmap IO, the current distance, not of the current distance. Or yeah, because we could find we find the minimum distance between left, up, right, down. So maybe it's not. Okay, let's say it is for now. Yeah, let's say it is for now. And then this is going to be DFS of mat I minus 1. Oh. So we do this. If hmap IO equals 1, then return hmap IO. And then we just have to run this 4 times. Yeah, this doesn't seem correct. So here would be I plus 1, and then here would be O minus 1, and then here would be O plus 1. And at the end we just return. I don't think this is gonna work either, but let's see. Oh, at least it doesn't take forever. Okay, so it's not updating the distance. Oh, it's this plus 1. Signed integer overflow. Right, because we can do plus 1 to the int max. What if we do instead? So it's gonna be LDFS. Int LDFS is gonna be equal to that. And then here, if LDFS equals to 1, actually no, if LDFS does not equal int max, then we get the minimum. Actually, we only need to do the HMAP when we're returning. It's fine. HMAP IO equals min between HMAP IO and LDFS. And then if LDFS equals 1, and LDFS plus 1 actually. If HMAP IO equals 1, return 1. Because that's the minimum you can get. And we just repeat this for all 4 directions maybe. So our DFS is gonna be, actually this is not LDFS, this is UDFS because it's up. Then this, if this is gonna be down DFS, DDFS, it's gonna be up a plus 1. What is this now? So the up DFS is I minus 1 0. If up DFS is not int max, then HMAP IO, it's gonna be equal to the minimum between the two. And then if it's 1, we return it. Down DFS is a plus 1. Then same thing here. Then left DFS is gonna be, actually let me just delete this. So you do up, down, left, which is gonna be O minus 1. And then RDFS, which is gonna be O plus 1. Extraneous for the DFS. Yep. The minimum between HMAP IO What if it doesn't exist? Then it would be 0, maybe? So maybe when we do this, we just make hmap io equals int max. Okay. Wrong answer. Okay, well now I'm thinking, what do we even need the hash map for? I don't think we do. We could just probably use the matrix. We could just update the matrix. Yeah, we don't need a hash map. We just we fill the matrix with zeros, and then, but that's the same thing we were doing before. We fill the matrix with zeros, and then we run the DFS on the ones. Or no, we can still do it this way. But we just have to pass it the answer matrix as well. Okay, we'll pass it the answer matrix. Okay. So here, instead of hmap.count, we just do if ans io equals int max does not equal int max. Then we have a cache hit, and then just return. Return ans io. If our matrix is a 0, then ans io is a 0. And return 0. Or ans io, I guess. We don't need to do that. So here we call mat ans here we call mat ans here we call mat ans, and here we call mat ans. Where else do I have hash map? Ans io. But this is for the final answer. Just go int min ans equal int max, and then instead of doing this, we do min ans equal min ans and udfs plus 1. If min ans is equal to 1, then there's no other possible minimum value. So ans io is going to be equal to 1 and return 1. I'll just copy this down. So down DFS, plus 1, down DFS, down DFS. Left DFS is O minus 1. And then DFS, LDFS. Okay. And then the right DFS. And it should be O plus 1. And then at the end we do ans io equal min ans and return ans io. Maybe? I feel like I'm going totally the wrong direction, but what line is this? 30? Oh, line 8. Oh, right here. Mat ans io. Okay. Stack Overflow. Last executed input. 0 1 1 1 1 1. So it's just a line down to the middle, and it's a 3 by 1 2 3 4 5. 3 by 5. Okay. 3 by 5. 1 2 3 by 1 2 3 4 5. And then 0 0 0 0 0 0 0 0 1 1 1 1 1. 3 by 5. Okay. Might be because of my conditions. UDFS, DDFS, or LDFS, RDFS, that's correct. I minus 1, I plus 1, O minus 1, O plus 1, that's correct. So it goes, checks up every time. It checks up, left, up, down, left, right. So this checks, okay. This goes to 0 immediately. This checks up, and then this checks down. And then it checks up, and then it checks down. I see. Maybe I can put some sort of like temporary value to be like, oh, I'm calculating this right now. No, I just think I'm doing it wrong. That you shouldn't go back to one that you visited previously. I don't know. Okay, it says BFS. Maybe you can't do it with DFS, or there's no like good way to do it. Okay, let's see. Maybe there's a DFS solution. Oh, you pass it a visited, which was what I was gonna try next, but it feels like too much work. Time limit exceeded, okay. So yeah, DFS is not the right, you have to do it with BFS, but then why was my solution so slow? BFS on 0 cells first. Yeah. Dynamic programming. Wait. To only have two directions, which are right and bottom. Oh, I see. O of n times n and O of 1. I see. So it's basically like the solution for... Actually, I'm assuming you're supposed to do this with like BFS, which I did. It was just slow. But okay, so better, like, I don't know, I'm just gonna put 100%. C++ solution. And then let me go back to this and let's insert it to the editor. Okay. Solutions. You push it. Result ij equals -1. -1 as it hasn't been computed. dx dy. Okay, I like this. Because this is what I do in Python, but I didn't know there was an easy way to do it in C++. This guy doesn't have a set for the ones they visited. Oh, you can do this too? Okay, I really need to learn, like, you can unpack values. You can unpack values, just like that, I guess. I didn't know this. So you check each direction. If nx is bigger than or equal to 0 and nx is less than n, result. And it equals -1 as in we haven't calculated it. Result n x and y equals result xy plus 1. Oh, so we update it just right away. And then we push nx, x, and y. So that's why it doesn't like go back. Because I used to have like a set to see which ones I visited. Result xy plus 1. So you start with the zeros and then you like spread them like in, and you update them right away. Because the previous way I was doing it... Okay. I see. And this beats 100%? Okay, let's see what I could change from this approach. So, DFS is just not possible, and I forgot this. I don't know why I tried so long. You need to use BFS to find the minimum distance, always. You can't use DFS, because you come into the problems that I arrived to. So we're gonna delete the DFS solution. Yes. And then we're gonna rename this one to 542.tvp. And then let's go in here and let's see what we could have done differently. So instead of having a set, we initialize it with -1, or I would initialize it with like int max. And here we push all. Oh, here we were pushing all ones. What was my original solution? This one where we push all zeros, and then we check the. Why do we do min adjacent? Yeah, we don't need to check all the min adjacents. We can just update it immediately because we're gonna go. Oh, that's what I did wrong. Okay. Let me do the solution. GP DGG. Okay. So here we don't need a set to check the ones we visited because we're just gonna be updating the value. We started them all with int max. Perfect. I just need to here in solutions. Okay. Okay, so it's already gonna be updated by the time we go in. Yeah, that makes more sense. So mat I, oh, it's gonna be equal to 0. And now let's try out the new technique we just learned. So it's gonna be auto cur x cur y equals q up front. I didn't know that one, but now I do. Matrix, if it equals to, no, we don't need to do this. We don't need to do the min adjacent because we already have the distance. We can do this dx dy trick, and that will reduce the amount of code that we have to write. Yeah, let's do it. So vector int dx equals 1 minus 1 0 0, and vector int dy equals maybe actually let me do it my way. We'll just call it dirs, and it's gonna be a pair of ints. And so here we're gonna have 1 0 minus 1 0 0 1 0 minus 1. Hopefully we can initialize it that way. Well, not queue empty, we do that. And then for auto dir and dirs, int auto dir x dir y is going to be equal to dir. So if dir x is bigger than or equal to 0 and dir x is less than n and dir y is bigger than or equal to 0 and dir y is less than m, and also we haven't visited it, so ans dir x dir y is not equal to int max, or no, it equals int max. Then what? Then we push that. We push int new x equals cur x plus dir x, and new y equals cur y plus dir y. And so instead of dir x and dir y down here, we just do new, actually, nope, new x and new y. And we push new x, new y. We don't need to insert them to the set. And we also need to update the value. So ans of new x, new y is going to be equal to ans of cur x, cur y plus 1. Here it should be ans IO. Nice. There you go, much better. So the whole time that it was taking like extra, it was doing the adjacency checks. Because before we used to have like you get to a position and then you check what's the minimum adjacent and then you update it. Turns out if you're doing BFS, you don't need to do the adjacent check because you're going to go from 0 and then start adding values positively. You also didn't need a set because you could check if you had filled in the value already. So there was a bunch of optimizations we could use. We weren't doing them very optimally before, but now it's much better, as you can see here. Okay. Let's fill in the solution. So, also, I like the techniques that I learned today. So how to traverse all the adjacent ones and unpacking values. And now another thing I'm wondering is if I really do need to use the auto. I don't think I need to use auto. So let's actually go over all of our auto keywords. So here it should be an int x and y. Each of our dirs should be, can I unpack it? Can I unpack them like this? Like right away? Is this possible? Let's see. If it is, it's awesome. Decomposition declaration cannot be declared with type int. Must be auto or reference to auto. So you have to do with auto. Okay. So we can't have an int, but can I do this? If I can do this, this is crazy. Oh. It seems you can. You can. Oh my god. I should study C++ syntax because I don't know all of this, and I feel like this is new, but like I should go over like the manual and see all of the new C++ syntax besides like this the standard container. There's a lot of these things that they added, and I use some of them. Like I use, like, for example, this for loop right here, and some other stuff, but like I should learn like C++ syntax deeply because this like makes your life so much easier. Okay, so this works. Right? Yes. Okay, so right here we're gonna write the answer. So we, is this car a 01 BFS? There's one way you can find the shortest path in single source and orders of resume breadth for search and a weighted graph. Distance is the minimal number of edges that you need to traverse from the source to another vertex. As a weighted graph, if not all edges in the graph have the same weight, then we need a more general algorithm like Dijkstra. If the weight is 0 or 1. Data sign and infinite set pair. Okay, so it's not a 0-1 BFS. 0-1 BFS is something different. Because in here, the weights can't be 0. Okay. So not 0-1 BFS. Let's not call it that. So we need to use BFS to find the distance, the shortest distance between every one and every a number and the closest 0. We start outward with all zeros and initialize their distance to 0. And add them to the queue. for every what do we say? For every neighbor that we haven't visited, the distance will be the current distance plus 1. We update set distance and then visit unvisited neighbors. BFS traversal order guarantees minimum distance. Okay. I think I need to go like now. So okay, I'm gonna push these really quick. I'm gonna go play Lorcana, so I need to leave y'all. $551. Okay, yeah, so I need to leave y'all. Let's push all this code that we wrote today. This is the console log 7, correct? Solutions. Add the console log 7 solutions. Hit push. Perfect. Okay, so yeah, today we solved a bunch of problems from Grind 75. We've switched from doing them like we were doing them where it was sorted by difficulty, so we're doing all the easiest ones. Now we sorted them so it's all rounded. So we're gonna start doing some mediums here and there, and that should help, and then we'll get to some hards and stuff. But yeah, anyway, thank you all for joining. Today we solved how many problems we solved? Like 3, 4? 5. We solved 5. I think that's pretty good. And I'll see you guys tomorrow for the next stream where we're gonna be doing a load balancer. But thank you all for joining today, and bye-bye.